perpendicular to the other coordinate or other coordinate surface, if this were a three-dimensional thing, it is the gradient of this particular coordinate, whatever, surface, hypersurface, volume, you name it. But here it's just a line. Q1 equal 100 has a gradient equal to that at that particular point. And then this one right here is perpendicular to the line that represents Q2 equal 200. Constant Q2, super 2 equal 200. Okay, so those are the definitions of these bizarre curvilinear that work in general. They don't care about whether it's orthonormal or not. This one happens to be orthonormal, but everything that we're saying here is going to be working for that. So the next few slides here, just go through this in piece by piece way, just showing what it is I've said. Each of the covariant vectors that you pull out of the columns of the Jacobian will give you a geometrical unit cell. Unit being sort of in quotes. And what it means is if the differentials were actually equal to 1, that's the vector you'd be talking about. It's based on the chain rule. Okay? dr is partial rq1, partial rq2. So taking those components is just what the doctor ordered to make E sub 1 and E sub 2. The contours are quite opposite. They're turned over, you see. This is partial derivative of R with respect to Q. This is the inverse of that Jacobian matrix called the Jacobian. And we pull off the rows of that to get those components. And that's what's going to be shown next here. But this is the basic idea of the covariance. Is that making sense? Is there anything here that trips your mind and says, I've got to figure out that, I'll figure it out at home? Figure it out right here. We need to get this kind of stuff understood right at the beginning. E1 follows tangent to Q2 equal a constant, since only Q1 varies in a partial derivative. That's the question you should have asked, is why did this happen, right? That's what a partial derivative is. All the other guys remain constant. Well, I'm looking at that guy. Only one is allowed to vary, so I'll put you on a tangent. Then the fact that that becomes the distance to the next unit of variation, where delta are 1, that's cool. That's really cool. Okay, let's go to the next guy here. The next line here, it says, I make a point for physics that these quantities, these covariant quantities, are best used to measure extensive quantities, that is distance, but also velocity, which you could quibble about whether that's extensive or intensive. But anyway. Okay, here's the other side, the contras, the dreaded contras with their red showing very well on this screen. They're not so red in the middle screen, but they're fire engine red down there on that screen. Okay. These are the guys that are normal gradients of their respective, in this case 2, in this case 1, variable equal a constant. So there's Q1, I'm sorry, Q2 equal a constant, 1, there, Q1 equal a constant, 100 right there, Q1 equal 101 there. Same deal here, but this sort of equation is not present here. These are all normal vectors that are being made here. Now, in really advanced mechanics, this is called the tangent space, for good reason. These things are all tangent to the lines that are of importance. And this is called the normal space, also with good reason. All of the vectors are normal to the whatever it is that is being constant. Okay, so gradients, normals. That's a very important idea. Okay, let's see if there's anything else I need to add to this. Well, yes, there's the bottom line here, basically. The contravariants are really quite useful for force and momentum, and that's what we'll be using them for. Canonical momentum will be covariant momentum. And that takes us back to Dublin. That takes us to the Hamiltonian. That's what the Hamiltonian is going to be making use of, is momentum, not velocity. Okay, velocity, that's Paris, right? Lagrange. All right? Okay. Now, here's what's really cool, is the co's are perpendicular to the contras. Just like orthogonal bras and kets are orthogonal in quantum mechanics, right? That's what that other space is for, basically. It's a secretarial thing, unless you have a orthogonal coordinate system and something complex and unorthogonal. These aren't complex necessarily, although we can play that game. We'll do that a little bit later. But this is absolutely a very important axiom, that M and N dot product, N contra and M co, always 1 and 0, depending on whether they are equal or not. It's 0 if they're not. Okay? So that I think is a key thing to remember in this. This is why we're doing this, because we're ready to work with really horrible coordinates that aren't orthogonal. Okay, so just very quickly here to remind you a little bit of what we've just said here, and also bring up what we've already kind of talked about, covariant metric, the actual dot product of M covariant with N covariant, that's this. That can be anything in these coordinates. If these are orthonormal, then this will be a delta function just like this. But this is always a delta function, no matter how screwy the coordinate system is, as long as you're not near a singularity, and that's, of course, a big catch with curvilinear coordinates. They make singularities all over the place. And Rick Hiller thinks that those singularities that you see are the walls that we see in our universe. The walls that have the stuff, and then there's vast regions that has nothing. That's something to think about. In any case, contravariants, they're in general non-zero to each other. It's only when the two get together they make this happen. Okay. Now this is a little bit like Lagrangian, Astrangian, and Hamiltonian. Okay, but we're not going to make that point because we're playing with the stuff that is more common to our physics and mathematics. Okay, so let's just take a quick look here at how it would be with polar coordinates. That's these guys right here. Here's the Jacobian. There's the columns that give us the covariance. Okay, and then I take the inverse of that and look at the rows, and I get the contravariants. Just write them out. There they are. And then go ahead and notice what the metric is. This is the metric tensor that's so important in relativity. This is the thing that determines length, but here we're using it to determine kinetic energy from velocity. That's the connection that this particular development of the Lagrangian mechanics is taking. So let's go and look at what happens when you actually use this for something, namely a particle existent in a two-dimensional coordinate system. There's the metric right there. It's just a very simple r squared for the polar angle and a 1 for the thing. So this little dot right here gave us an r squared. Okay. And this is the Lagrangian potential, not specified now. We'll do plenty of that later on. Our oscillator will be our first potential to really look at motions inside your sophomore physics earth. Okay. But here's where the metric goes. Once you get this metric, it's so easy to get these, take their dot product, bingo. There's your Lagrangian. And you may have a potential that's a function of both R and phi. If it's so, there it sits, and then we're going to be doing the equations that go with that. Okay? Now, what we probably ought to see right away is a thing called canonical momentum. And we know how to get that pretty easily. And there it is, for one coordinate. This particular one is not very surprising. R is kind of an orthogonal like coordinate. So when I go and use GRR, I put a 1 in for that. Okay, it's only when I get something that's a function of where you are that it gets squirrely. And those are the Coriolis, centripetal, centrifugal, and all that stuff. That's going to fill this space as we finish this lecture. Okay, but this one, no surprise. M R dot. That's radial momentum. Radius is kind of not having any problems right here. But the next one that we'd like to look at here is the momentum. Okay. That is the partial derivative of the Lagrangian with respect to the velocity. Okay. So let me put that on all three screens here and remind you of our Lagrange's equations, which is what we're working out here in detail. And this one is a wow. You know, if this is the first time you've seen this, and you've gone through sophomore physics and wondering, what the heck is it? What's this funny inertia, mr squared, blah, blah, blah? Well, that's where it comes from most easily. There's mr squared phi dot. That's angular momentum. Bingo. Really neat. And you see, this is going to work for crazy coordinates, okay? Queer coordinates, right? You're going to be able to get the momentum that goes with that particular coordinate very easily. Okay. So this one is giving you a moment of inertia, rotational inertia. Angular momentum is a product of that with what we would normally call omega phi, phi dot, angular velocity. Okay? All right. Let's try for some torques and other forces that would come up here. That is what's going. So this is just from the preceding page. Let me jump ahead and actually work those out. Okay? So that's from just what we just did. And here is the next step here. Here, total time derivative. Okay? This equation involves total time derivative for each r and phi momenta. Okay? Here's p dots. It's the partial of L with respect to r. Here's L. I see an r right there. And remember, partial derivative just treats everything as a constant except r. And I see an r there. Maybe. Depends on whether my potential actually depends on the radius. If it doesn't, I would not have worry about that. Okay? But this one will always be there. And that's a curvilinear effect right there. We're actually taking a partial derivative of the metric coefficient g phi phi, and we're getting this. And then if the potential is a function of r, we get something subtracted from that. Okay? Well, that's another wow. That's a centrifugal force. mr omega squared. Well, mr phi dot squared, that's the same thing. Okay? That's cool. And if it wasn't that, you'd check some arithmetic mistake, you see. Very often you can go and do that. Now this one, if there's nothing in here that's a function of phi, I wouldn't get anything from the kinetics. There's no phis in there. There might be one there. you got a wavy potential or it goes around the circumference, you're going to have to take that gradient, that partial L with respect to phi. Okay? So, at this point, we're sort of half done with actually writing these equations here. The partials with respect to the coordinates. But also the partials with respect to q dots. But to get the actual, to finish this out, we got just a tiny bit more work to do here. To find p dot directly, and that's what I need to do next here, find the p dot directly from the first Lagrange equation, this thing. This is a time derivative of what we call momentum, p phi, or else pr. We got to take the total time derivative. In other words, now, when I take the derivative, it isn't just look at something that has a t on it. We look at everything. So, as I take a time derivative, total time derivative, I even worry about the m. Does the m have any? Well, no, we don't have it being anything but a constant. But this guy's got an r in it, so I got to worry about what r dot is. And then this guy, phi dot, I got to worry about it too. All of those give me possible contributions to a total time derivative of that particular quantity. And then, of course, this one too, but that one's easy by comparison. If you look at that, there isn't much going on here when I take to calculate that one. But this one, okay, same thing. Now, it happens here that the p dot for this is just a partial L with respect to phi, and if we don't have any explicit dependence on the potential, I'm golden on that one. This is a conserved quantity. Call it script L or something like that for angular minimum conservation. But the finishing this thing, where I really have to take the time derivative of that's the part that gives you a few more terms that you have to worry about. So let's go ahead and do it first on this screen, and then on this screen, and then we're done for the day. But we've got to talk about these. These are not quite so simple as the first half of the analysis of the Lagrange equation. So taking a derivative here of the momentum, actually an explicit expression for it, that's a pretty easy job. Okay, so I will just get mr dot dot for p dot here. Now, if you work out let's see if I've got that right. If I work out, this thing, if I ask the time derivative of that thing, okay, this is what it is. I've got an mr phi dot squared. That was centrifugal force. So after we get this finished here, we actually figure out what r dot dot is. That's the whole story right there. And let me go ahead one step on this one step on this one, and one step on this one to finish the dots. And look at p dot phi right here. That's the non-trivial one. As I go to take the time derivative of this, I get two terms. One of them involving a derivative of this, which gives me a factor of 2, and then r times r dot, that's r squared, being differentiated totally. And then the next one is the derivative of that, phi dot, is phi dot dot. Okay, so there are two really important terms right there. And this is the Coriolis effect. Okay, so that again, I say wow, because Coriolis is really kind of a tricky thing to deal with, as I pointed out when we just sort of hand-waved our way through its discussion. This is very quantitative and very simple. It's admittedly only in 2 dimensions, but you'll see when I give you a problem with 3 that it's really quite easy to do all of this and calculate these quantities. Now, we have something to do here, I think, that's really germane at this particular point when our southern friends are having an awful time because of one of these damn things. But what really causes the disaster, shall we say, that a hurricane provides? And I'm going to go ahead and advance this one by maybe one step, and I probably can do it here as well, just to give you a feeling. Because this is an equation, this particular one right here that we just calculated, and let's just assume we don't have any potentials here, we don't need them. We've already got the whole thing moving at some particular value. Now what we're doing here is I'm saying this thing, if I get the m's out of there, divide by r squared, kill that r to get 1r, and forget about that. That's the key factor right there. It drives our weather. We're on a rotating globe. It's got a velocity phi dot. The phi dot is this way. Okay, we're looking down from the North Pole at the Earth. It's going like that, right? You go around the thing and the sun rises, right? And then the sun sets, right? Talking like a northerner. Now, if this was by an Australian, we'd have it going the other way. Then we turn other things around as well. Let's just stay up in the north, okay? We've got phi dot greater than 0, and we've got r dot. Now, here's the deal. You get a low pressure area anywhere, and the atmosphere suddenly says, hey, there's something going on here, we got to go for it. There's stuff pushing on us. We've got a low pressure region. Well, when that low pressure region starts to bring the air in, this is the equation telling you what's going to happen to your phi dot. It's going to get dotted again, and it's going to be -2. Okay, but this is minus, that's positive, so you're going to get a positive rotation. This is going to make right-handed. Now, I like to use the quantum mechanical view of this thing, and I think I've got that actually written at the bottom there. Might as well put it here too. Deep quantum rule, flow tries to mimic the external rotation. In other words, reduce the relative velocities. Because relative velocities is like a beat of the waves, and that's high energy. You want to get that, low. Nature tries to get that low. So the easy way to remember is which way things are going to be turning due to the rotation of the Earth. They're going to turn in the direction of the rotation. And we'll see that more clearly with these various rotational demos that we'll show later on. But that's really something to know. And the other thing is that this whole system, on the average, moves, if it's not violent like the one that's going on in the Carolinas, it will move with the rotation of the Earth. That is, our weather systems come from the west, pass through, and when they're approaching us here, something out in Oklahoma or Colorado is coming and it's strong, you're going to see a nice warm south wind preceding that storm. When the storm gets here, you're going to see the wind shift, and as it goes away, you're going to feel a nice cool breeze from the north and clear air usually. Okay, so that's just an ordinary weather system. This hurricane is an extreme case of that. Very extreme. I mean, that extreme. Okay, and this is from Ima, the Hurricane Ima. But Florence is actually the same size as that. It's giant. So right now they're getting all of that water off of the ocean coming and dropping in the middle of the state. And I guess the latest count was something like 5 feet of rain. And these are, you know, kind of record-breaking for this country. You go to India or any of the continents that have typhoons, they broke that record a long time ago. And they get them more often. And they're just like we are getting them more often because the water has warmed up. Okay, well, we're right on time, almost, for this. And this is enough said. I think I've tried to give you the idea that the Lagrangian is a powerful tool. Hamiltonian is too, but very different. It uses covariant quantities. None of this contra stuff. Okay, we'll see you next time.